Hi everyone, this is our waste classification project for the final project. My name is Julia Reinhardt and my teammates' names are Emil Nava and Carlos Saceres. Okay, so I'm going to go to the next slide. So waste classification using deep learning was what our project was on. Our goal was to classify images into 9 categories, being it paper, metal, cardboard, food organics, glass, vegetation, textile trash, miscellaneous trash, or plastic. One of the problems we encountered is that our data set is small and slightly imbalanced. So one way that we went about this was stratified splitting instead of a random split and data augmentation to increase the size artificially of our data set. Possible applications to this are that when doing a beach cleanup or whatnot, we can more easily sort trash and things of that manner. There are various applications, maybe with robotics as well, just to facilitate sorting trash without needing a human being there, but letting the machine learning model achieve that task. Okay, so our high-level solution was that we started with the RealWaste image data set. Then we completed our stratified train validation and test splits. Next, we did data augmentation, and then we modified our approach using 3 models, the CNN model, YOLO version 8 classification, and also YOLO detection. Our results were also displayed with confusion matrices for accuracy and loss. So augmentation was only applied to the training data images so that the model could learn better. And we also evaluated accuracy and loss curves with this method. So stratified splitting matters because, as you can tell from the graph, our categories are not exactly equal or uniformly distributed. They're different amounts within each category. So stratified kind of matches those proportions so that our validation test split results become more reliable. So it matches the amount of data within that split. Okay, and then next, so the code that we did to implement the stratified split was over here. All we had to add was the stratify parameter equal to targets and stratify equal to temp targets in our CNN model. Now, data augmentation as well was another method we used to improve generalization. That's because, again, our data set was small. It was just under 5,000. So some examples of data augmentation, we did small rotations, horizontal flips, and scaling or zooming, and also brightness and color adjustments. So here's an example of what a horizontal flip does for data augmentation. As you can see, it's the original image, just horizontally. It's completely flipped. All the other parameters stay exactly the same, and it's an easy way of diversifying our training data for the model. So the model doesn't memorize the training data, which can lead to overfitting, but it actually learns from the data and can then apply it to new situations. Okay, and here's the code to implement data augmentation. So here, as you can see, we just needed to add this code for our CNN model, and we added our random resize crop, horizontal flip, random rotation, color jitter, random perspective, etc. And so basically what this does is it's applying random cropping, flipping, rotation, and lighting adjustments and normalization to create our image variations, which will then improve the model generalization and combat against overfitting. And my teammate will continue the next section of this model. Thank you.